All right, so we are now recording. Let me get the screen share up. And we're in 7.5 now, so here it is. I opened 7.6, but I don't see it, so I'm going to have to go back and open it again, but I'll wait until we get there. Okay, here's 7.5. And let me scoot over Kira. She's, of course, in the way here. Okay. And let me find which slide we're on. Excuse me just a minute. I didn't turn on my overhead light. I'll be right back with you. All right, sorry about that delay, but I was rushing back in here after lunch and forgot to turn on my light. Okay, my stuff's falling off the desk too. Okay, so I was trying to find what slide we were on, and it looks like we were on, because I don't see a mark anywhere, work done by a variable source. Does that sound about right to you? There. Okay. And let's go on and get this open to current slide. And let me get this thing scooted out of the way if I can. Okay. All right. So any more questions, issues, concerns, anything before you want to get started today? All right, a little bit of review of where we are and where we are going. We're in Chapter 7, Applications of Integration. We've talked about several applications. Now we're dealing with work. The work done by a constant force didn't require any calculus at all. That was the first page in Chapter 7.5. Now we're getting into where calculus comes into play. Work done by a variable force. Okay, let's pause also a moment for where we're going from here, because we are frankly running out of term. Hopefully we'll finish 7.5 today and get going in 7.6. And I haven't decided yet. I think we have to do 7.7 too, because some of you may need. They're fairly short sections, so hopefully we can move along through these pretty quickly, and then I'll give you the Chapter 7 test, hopefully before the end of this week. That only gives us next week, basically, to wrap things up, and we're going to get into Chapter 8, which is Techniques of Integration, which I wish we'd gotten there sooner, because that's, to me, the heart and soul of Cal 2. Integration and techniques of integration. So we'll try to move as rapidly as we can through the last remaining sections here, and then get into Chapter 8, and at least get you at least some tools that you can use for future courses. It really irritates me badly that they cheated us out of 3 classes this term. They start a class on a Thursday, which I asked them, please don't do that, because before we ever met the first time, Tuesday, Thursday classes already had 1 week under the belt. So we were behind a week on our first day of class. Then they gave us the Monday of 4th of July weekend rather than the Thursday as the holiday. If they'd have just done Thursday, we'd have made up one of those days but Tuesday, Thursday classes got a week and a half ahead of us then. And then they've shortened the term. Normally we go until the first week in August. Now we're ending on the 23rd of July. So we don't have much time left. So sorry about that. Let's move as fast as we can. And here I am just flapping my gums. Okay, so let's move on to work done by a variable force, except it won't advance for some reason. Now it does. When a variable force is applied to an object, calculus is needed to determine the work done because the amount of the force changes as the object changes position. For instance, the force required to compress a spring. If you had a spring here, you're trying to compress it. That first little amount of compression you do doesn't take much force at all. It takes some force, you have to push on it, but then the more you push, the harder you have to push to get it compressed any further. That's a variable force, okay? Same thing with stretching the spring. If you're stretching a little bit, yeah, it doesn't take that much to do a little bit. Try to stretch it more, and it's more force to stretch it. So, for instance, the force required to compress or stretch a spring as the spring is compressed increases. Okay? Consider an object that is moved along a straight line from A to B, okay, by continuously varying force F of x. That's why force is a function of x. It's not a constant force anymore. So let's let del, our good old delta there, that's a capital delta I think, be a partition that divides that interval between A and B into n subintervals as determined by the first one, x sub 0, that's your A, and then you have x1, x2, x3, x4, all the way up to x sub n, which is also your B. So we've divided into that. That's your the delta, your partition, and let the delta x sub I, any one of those, between any two of those x sub i's, between x sub I and x sub I minus 1, that is your delta x sub I. And for each I, 0, 1, 2, 3, 4, 5, 6, all the i's that you have up there, choose some value in that interval, c sub I, such that c sub i's are between x sub I minus 1 and x sub I. Okay? So some value in the middle. It doesn't have to be the center value, though that's what it sounds like. It's just some value in between the two ends of delta x sub I. Then at c sub I, the force there is F of c sub I. So if you have a small enough interval, the force between this place and that place isn't going to be a lot, but it'll be a little bit. That's a variable force. So we're just going to take to F at that, let's just call it a center value, though it doesn't have to be in the center. But because F is a continuous function, it's not jerky, it doesn't change as you go that way. It's a continuously changing function, a smoothly continuous function. You can approximate the work done in moving the object through the ith interval between here and here would be the F of c sub I, that work in the force in the center, times the distance you moved, which is your delta x sub I. Okay? So we'll just assume that you're moving from here to there. Okay? That's your delta x sub I, if you want to call it, and somewhere in that is your c sub I, and whatever the F value is at that c sub I in the middle there, or somewhere in there, that's going to be what we approximate the force to be in that entire interval. Okay? So the total work done to move from A to B would then be summing all those up. The sum of those incremental works as you do the work just to go from one delta to another delta. Okay? So you're going to sum up as I goes from 1 to n, your delta W sub I, which the W sub I from up here is F sub C sub I, the force at some point in that W sub I, times your delta X sub I. And do that for every increment that you have in there. Sum those up, and that's going to be approximately the work done in that interval from A to B. Okay? So, that approximation appears to become better and better and better as you let your delta, your norm of that partition, go to 0. In other words, your n is going to infinity. Now the norm is the largest of those partitions. Like if this was a little bit bigger than this one here, we'll choose that big one, okay? But then as you get more and more of them, even that big one's going to get squeezed some. So as the norm, the largest of those partitions goes to 0 as your n is going to infinity. So the work done then would be the limit as that norm goes to 0 of that summation of I equal 1 to n. Remember, n is going toward, oh, here comes somebody I can't read. It's Joy. So let me get Joy in here. Okay. Let me get those up there and get Joy Robinson here. Whoops. Already had Joy here. I'll put Aaliyah in Joy's spot. Aaliyah, get out of Joy's spot. Okay, what were you thinking? Okay. All right, there, I've got them both here now. Okay, stay where you belong. Okay, all right. So the limit as that partition the norm of that partition gets going to 0 of your summation of this then becomes your integral from A, which is when the I was equal to 0, to B, which is when I is equal to n, the integral of alpha of x dx. And that's all it is. Seems like they could have said that right at the beginning and we could have gone right on to it. Okay. Now it won't advance. Okay. So here's the definition. This is in the box near the bottom of page 486. I didn't tell you that, I guess, but that's where we are. Definition of work done by a variable force. If an object is moved along a straight line by a continuously varying force, f of x, so the force changes as the x changes, then the work done, and it's a continuously varying force, no discontinuities there, nice, smooth, continuously varying force, then the work W done by such a force as it moves from x equal a to x equal b, this end to that end, is given by W is equal to that limit, if you want to do that way, or the integral from a to b of f of x dx, just like we said before. All right, now, before we move past that, there is a little blurb here about Emily de Bretteville or something like that. I don't know how to pronounce her name. The major work done by her was a translation of Newton's Principia, if you remember that, into French. Okay? Her translation and the commentary, she didn't just translate, she also commented on it, greatly contributed to the acceptance of Newtonian science in the mainland part of Europe. Of course, Britain followed it all the way. But remember, in Germany, there was Leibniz, who was claiming he came up with the whole idea. Well, Emily de Bretteville, or however you say it, her French translation with commentary, added some to it that greatly enhanced Newton's standing in continental Europe. Otherwise, it would have been the English Channel dividing the two. But she really contributed big time. Very, very unusual for a woman at that time. So I don't think I'd ever even heard her name before I started teaching from this text. Okay, so let's move on. Work done by a variable force. The following three laws of physics were developed by Robert Hooke. The first one, Isaac Newton, lots of them. The second one. Now notice Hooke was about 7 years older than Newton, and he was a well-established scientist in England at the time Newton was just completing his university training at Cambridge, I think it was. Newton came in like a ball of fire, and Hooke, who was the good old staid and rule bound, and things just progressing on a nice normal pace, here came Newton, just overturned apple carts as he went, apples falling from tree, all that kind of stuff. So that's they were somewhat contemporaries, though Newton was younger than he. They didn't, I don't think, got along too well. I think Newton did not have much time for the old staid way of doing things. He wanted change. That's what calculus was all about. So anyway, there's the second, and then the third one was Charles Coulomb over in France, and he was born after both of them had died. He was mostly in electrical areas. So we're going to look at these three. First, Hooke's law. And here's what Hooke's law says. The force required to compress or stretch a spring, like we talked about, within its elastic limits. Okay, you know, if you've ever played around those little springs that are in your ballpoint pens, if you even remember what ballpoint pens were, that when you clicked them, you know, they came in. If you ever played with that spring, if you played with it too much and stretched it just a little too far, it didn't return. It passed its elastic limit. What elasticity is returning to the original shape. You compress something, it comes back. You stretch something, it comes back. If you ever get to the point where you stretched a little too far and it doesn't come back, you pass the elastic limit. So that's why they threw that in there. The force required to compress or stretch a spring within the elastic limits is proportional to the distance that the spring has been compressed or stretched from its original length. So here is the simple expression of Hooke's law. F is equal to KD, where first, F is the proportionality constant. We often call that the spring constant. Occasionally you'll hear people call it Hooke's constant. It depends on the nature of the spring. For instance, the slinky would have a very small spring constant. The coil spring in your car would have a huge, enormous spring constant, because it's going to take a lot of force to compress that coil spring in your car at your car wheels, whereas a slinky doesn't take much at all. So that's your constant proportionality, or the spring constant. The second of these is Newton's law of universal gravitation. This is just one of many, many, many of Newton's laws. The force of attraction between two particles of masses m1 and m2 is proportional to the product of the masses, inversely proportional to the square of the distance between the particles. And here's his formula. F is equal to, that's called the universal gravitational constant. Now don't confuse that with little g, which is the acceleration due to gravity. This is a constant of nature. Okay, doesn't depend on what field, force field, gravitational field you're in. It's a constant of nature. M1 times M2 divided by the distance squared. Okay, I take that back. It does sort of depend. We won't go into that. When M1 and M2 are in kilograms, which is usually the units we use for mass in the SI units, System International, D is in meters. A kilogram is a pretty large mass. A meter is a really long distance for these kind of measurements. F will be in newtons. Force is in newtons. When your G is 6.67 times 10 to the minus 11th cubic meter per kilogram second squared. Okay, now what in the world is that? Well, you know, they've left something. Well, no, they haven't. What is a newton? A newton is a kilogram meter per second squared. Okay, so that's what you've got on this side. What you've got on this side is a kilogram and another kilogram. And this is a kilo. Okay. Boy, I think I'm going to have to write this one out. So let's go to our, I don't know. Are y'all that concerned with the units? I know if you're a physicist and an engineer, you probably should be. So let me do those. Now here is the second thing, the third thing that may have had an issue over the weekend. It hasn't yet, but my Wacom pen rolled off the desk. I usually keep it in a little tray here. It must have fallen from the tray, and when I walked by to get a book off the bed here, I'm in a bedroom, I bumped into the desk and it got the pen rolling. It fell to the floor. These are really sensitive. I don't even know if it's going to work. Let's see if it does. If not, we're in sad shape. So let's go to the whiteboard and let me get this thing scooted out of the way here. That's the taskbar. You probably can't see it, but it's in my way of writing on the whiteboard. And then let's scoop the whiteboard over as far as we can so we have as much white space as possible. Okay, so let's see if this works now. What we had was F is equal to, yeah, it works, I think. Okay, good deal. The force due to gravity, F, and that's measured in newtons, I'll work with the units later, is equal to G times M1 times M2 divided by D squared. Okay, now remember, force is in newtons, and a newton is a kilogram meter per second squared. Okay, now over here we have a meter here, a kilogram here. I was providing the mass here. A kilogram there, and then another kilogram. Kilogram times kilogram divided by meter squared. So, in order to make the units make sense, then this G has to have a per kilogram in it, so it can cancel one of those out, and then you have kilogram on this side, kilogram on this side. It has to have a meter cubed here, which is such a pain in the neck. Okay, a meter cubed here, so this per meter squared here can cancel that out. Okay, now we have a kilogram meter, and we just need a second squared down here. So this unit also has to have a second squared. So what are the units for G? Meter cubed per kilogram second squared. That way you get newtons on this side and newtons on that side. Now most of the time I hear it called a newton meter squared per second squared. That's, to me, a lot easier to do. If you just went on and called this a newton meter squared per second squared, per kilogram squared, I said it again, okay, then when you multiply this by those two, these go out, and multiply this by that one, it goes out, and you're left with newtons on both sides. So that, to me, is the easier unit to deal with. But since the book used meter cubed per kilogram second squared, that's what I wanted to show you. How in the world did they get that? Okay, so here we go. Remember that, meter cubed per kilogram second squared. Let's go back to here, and we'll see. This is such a pain in the neck from current slide. Okay, where G is in cubic meters, meter cubed per kilogram second squared. That's exactly what we got. G is called the universal gravitational constant. Okay, and it is universal. If you were on Jupiter, if you're on the moon, if you're on an asteroid, if you're wherever you are, that G will work. If you use the little g, every gravitational field you're in has a different acceleration due to gravity. This capital G is universal. Okay, and then finally Coulomb's law actually looks a lot like Newton's law of gravitational attraction. The force F between two charges, Q1 and Q2, in a vacuum is proportional to the product of the charges, Q1 times Q2, inversely proportional to the distance between them squared. That proportionality constant is K, often called Coulomb's constant, or the electrostatic constant is what we call it, because this is called electrostatics. The charges are fixed, they're not moving. Now, and how in the world, why they changed the units, I don't know. This is not a physicist doing this. Most of the time, F is in newtons. Okay? So I don't know why they said this, but here's why. Because they said D was in centimeters. Now, the only reason really to do this, physicists use D in meters, okay? But electrostatic attraction is stronger than gravitational attraction, but gravitational attraction will go over a much bigger distance than electrostatic. So that's why they're saying D is in centimeters. Well, if you make your D in centimeters, then your force has to be in dynes, which is a smaller unit than a Newton. Okay. And why they say for a value of K equal 1, I'm not sure. You know, this is a math book. So let's not spend too much time with that. I don't know why they say that. Okay, so let's move on. Here's example 2. We already did example 1 back on constant force. Here's example 2. A force of 30 newtons, and this, by the way, let me move my things around a little bit. Okay. Now, this example, by the way, even of those of you who do not have this text, if you're using your calculus book from your home campus, then you can still go to larsoncalculus.com and see an interactive version of this type of an example. I think it's this exact example, but I haven't checked them all out. A force of 30 newtons compresses a spring 3/10 of a meter from its natural length of 1.5 meters. Find the work done in compressing the spring an additional 0.3 meters. Now, what in the world are they talking about here? Well, the first part here, a force of 30, let me see if I can get this to show up here. I think I can. Yeah. A force of 30 newtons compresses a spring 3/10 of a meter from its natural length of 1.5 meters. Now, why did they tell you that? They told you that because they didn't tell you the spring constant. This way you have to figure out what the spring constant is. Okay? Now, once you know the spring constant, then you can find the work done in compressing the spring the additional 3/10 of a meter. That's beyond the 3/10 you did to get your spring constant, another 3/10 out of that 1.5 meters. Okay? So let's go to the now let me try this. Since my pen did show up there, what do you think of let's trying to work it here? Okay, now what we know is Hooke's law, which they gave us before, as this. F, now this is very fine. Can you read it okay? F is equal to KD. Now, I said D and wrote G. Let me see. I don't have an eraser on this screen. That's the problem. I knew there was some. Sorry about that. We will go back to this. The whiteboard. It has the eraser. And I do tend to make mistakes, as I'm sure you find is very shocking to discover. Okay. Let's just clear all drawings here. Okay. And write. This is Hooke's law. F is equal to KD. This time I'll write a D rather than a G. Okay. Now, what we need to do is find out find out K. So K, if you divide both sides by D, K would then be F over D, which would be, and they told you 30 newtons oops, that'll go away in a minute I think, divided by 0.3 meters. Okay, now, oh, here comes Jalen. Let's get Jalen in here. Hold on a moment. Jalen's here. Okay. Don't know if made it into audio yet because I can't see that, not when I've got all this other stuff open, but hopefully we'll be here soon. So Jalen's here, I hope can hear. Okay, good, welcome. All right, what we're going to do this by hand, you could do it on a calculator too. Move that decimal one place there, take this decimal here and move it one place there, and then you got 3 in the 300 would be 100. The K would be 100 Newton per meter, and that's a good unit for your spring constant. By the way, Jalen, we're in Chapter 7, Applications of Integration, Section 7.5, Work. We're in the part of work called the variable work, and this is example 2 near the bottom of page 487 if you're using the same book that we are using. Okay, so that's your spring constant. That's the first part of the problem. The whole reason for it was so you could calculate the spring constant. Now that we know that, it says find the work done in compressing the spring an additional 3/10 of a meter. Okay, so basically what we have here, the work done is equal to the integral from the first position to the last position. Okay, now the spring was originally and this gets just a little bit tricky with Hooke's law. Okay, so remember the spring was originally 1.5 meters length. We compressed it to begin with 0.3 meters, and now we're compressing it again another 0.3 meters. So where we're going from here, and this is all they're asking about, how much work did it take to do an additional 3/10 of a meter? So you're going from a compression of 0.3 meters to a compression of 0.6 meters. And then your f of x, here it is, that would be k times x. Well, the k is your spring constant, that's 100. Now if I had left enough room, I'd put the units there too. I don't have enough room. Times x dx, because x is the amount of compression you're going to be doing. So it's 100 times your compression, and the compression is x. Okay, now setting up the problems, really the harder part. Doing the calculus is the easy part. This would be 100, this time I will put my units down, Newton per meter, and then you do the antiderivative of x dx. What would that be? Anybody? Yuck, such a pain in the neck. X squared, you increase the exponent by 1, the simple power rule, and then divide by the exponent. And we evaluate that between 0.3 and 0.6. Remember, that's evaluated in terms of meters, because that is how much you compress it initially to 0.3, and then you compress it an additional 0.3, which got you to 0.6. Okay, so let's plug and chug here. That would be 100 Newton per meter. I don't really have to carry those units around, but I think it, for you who are going into science and physics and engineering, you need to get used to keeping up with your units. Okay, let's plug in and see what we get. 0.6 squared is 0.36. But wait. Let's take this 2 out here into the 100. Okay, and just make this a 50. Yuck. Make this a 50 out here. I just pulled this 2 out and divided 2 into 100. So I don't have to carry that around anymore. So all we have is x squared, so 0.6 squared is 0.36 minus 0.3 squared is 0.09. Okay, now these are in meters squared because these were meters here, so these are meters squared. Whoa, here comes Houston. So let me get Houston in here if I can get my pen to do it. There he is. And let me get him in the roll book as well. Okay. I guess in an email recently I got from Houston, I found out he's working full time and he comes in during his lunch break. So welcome. What a good thing for lunch. Okay. All right. And here also comes Jesus. So let me get Jesus in here. I wonder if you're on your lunch break. Okay. Here is Jesus is here. All right. Good deal. Turning out to be a bigger class. That's good. All right. For those who just come in, Houston and Jesus, we're in Chapter 7, Applications of Integration, 7.5, Work. And we're in the part of 7.5, which is work done by variable forces. We're doing example 2, bottom of page 487 if you've got this book. If you don't, you can also go to larsoncalculus.com for an interactive version of this type of an example and see it. Even if you do have a book, you can still go there. Okay, so let's get our handy dandy calculators, which for me is my telephone. Okay, and pull the calculator up here. All right, clear what we got on the screen there, and have 50 times, I'm going to have to open parentheses, so I'm going to have to turn my calculator sideways, open parentheses, the difference between 0.36 and 0.09. That I believe is 0.27. I didn't need parentheses because I did that in my head and it didn't take it anyway. Okay. All right, I got 13.5. I think that's what the book got to. Yes. And what are your units here? Okay. Well, we see newtons per meter here. This was meters squared here. So that was 13.5. Okay, pretty ugly 5. Newton per. And you had meter squared here and meter here, so not per anything. Newton meter. And what is a Newton meter? If any of you have had physics yet, you know a Newton meter is a joule. That's an ugly 5 again. 13.5 joules, and that's exactly what the book got. Okay, now their illustration in the book does a little bit more than what I did, and I hope you're looking at that. I'm trying not to drop my pen again. Okay, here's the deal. You started with a spring at a certain, just there in its normal state. To get the spring constant, we compressed a little way to find out what the spring constant is, and then the question is to do that middle one to get to the last one, what would be the additional work required, and that's what we just calculated. Okay, now I think, they have this on the other page. Any questions before I close the white page? So let's see, we're up to 11 students here, so let me make sure I've got enough in the book. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, yeah, because Amina is on with Laron. Okay, so let's go back to 7.5, and we have to go back to current slide, and here we go. So, by Hooke's law, the variable force, F is a function of the displacement, required to compress a spring, x units is F of x is equal to kx. I didn't write that down before, I just put it in my integral that way, but that's your F of x. That's Hooke's law. Okay, Um, and they didn't actually write that out. They say KD, but X is the measure of your displacement. Okay. Now, because the initial displacement, 0.3, required 30 newtons to do that, we used Hooke's law to determine what your K was, and they got the same thing we did. K was equal to 100 newtons per meter. I like to carry around units. Okay. So then, and here's that figure I was showing you. I didn't need to hold it up. Here it is. So for f of x equal to 100x, because that's 100 was your K, now we know the formula, but now we're going to compress from 0.3 to 0.6 meters. Okay. So to get the increment of work, assume that the force required to compress the spring over the small incremental distance, delta x, is nearly constant. Okay. So they're going through all the delta W thing here. So the increment of work on the very small part would be the force times the distance increment. Okay, that's 100x dx, or delta x. And because the spring is compressed from 0.3 to 0.6, less than the natural length, the work required is this, exactly what we did. This is the basic formula. Work is equal to the integral from a to b of f of x dx. We had from 0.3 to 0.6, 100x, that's your f of x dx, and that's 50x squared from 0.3 to 0.6. And when you do that, you come up with 13.5 Newton meters, which is a joule. Okay, they didn't explain what those equivalencies were, but that's exactly it. Now, note that you did not integrate from 0 to 0.6 because you were asked to determine the work done in compressing the spring, the additional 3 meters, 0.3 meters, not the including the first. If it had said what was the work done to compress from 0.3 to 0.6, from 0 to 0.6, then that's what you would have used. You still had to use that first 0.3 to determine your spring constant, but then if you let that relax again and then go back and do it, or even if you said what was the work done to do that first 0.3 of a meter, once you knew what the spring, well, you already knew the force, so but you didn't know the work, so this formula gives you work. Okay, the summation of increments in the form of force is equal to distance increment. That's what we were just doing. Another way to formulate the increment of work is delta W is the force increment times a given distance. And that's your delta F times X. That second interpretation of delta W is useful in some problems involving the movement of non-rigid substances such as fluids and chains. Okay, one of the classic problems is you drop the length of a chain down a hole. Now that length, the gravity from that length, before the surface was holding up that, you didn't have any motion. You drop one of them down, now gravity's pulling that down and it starts pulling more. But then the more you get down there, the stronger the force due to gravity, so it moves at a faster rate. Now I was in the Navy and I witnessed this, unfortunately, on the forecastle of our ship. We were doing a inspection and survey test of our anchor windlass, manual anchor windlass brake, which you hardly ever use, and since it had been at least 4 years since it had been tested before and never had been used since, and who knows if it was tested 4 years prior, but it may have been. They went to test it and they would release it and then have the guy crank down on it, and the first 2 times he was able to get it to stop, but that third time when more of that chain was, and those are big change, each length of several tons, so that was really pulling down. He cranked down on that anchor windlass brake as hard as he could. It would not, it may have slowed it a little, it would not stop it. That thing got going faster and faster and faster, and then The whole length of chain went flying out. They call that last link the weak link. They make it a little bit less strong than the others are. It pulled away from the bulkhead. The whole anchor, the chain, everything went down into the water. Okay, deep water. And we went in with only one anchor, and the captain was really furious. He said, we're the one-eyed wonder here because there's an anchor on either side, and it was pretty embarrassing. But I witnessed the delta F times X. Okay, the change of length. So that's for non-rigid substances. Also works with fluids. In fact, we'll be working mostly with fluids. So here's example 4. They've skipped, sorry, example 3. Okay, I guess we ought to do it. So let's go back to 3. That's before we get to what we were just talking about here. So let's go back here and do example 3. Sorry about that, I wasn't paying attention. Okay, let's clear the screen from all of our scratch, and let's do example 3. A space module weighing 15 metric tons on the surface of the Earth. Okay, so let's call that the weight. That's also a force. Weight is a force due to gravity, and sometimes you'll see it called F sub G. Other times some books will call it F sub W. Sometimes they'll just call it W for weight. Let's just call it F sub W, the force due to weight, and that stinking thing will not write. Okay, force due to weight is 15 tons, 15 metric tons. And I'm going to call it MT for metric tons. That's not exactly the way you should say it, but I'm going to do that so I don't have to write it out. On the surface of the Earth, how much work is done propelling the module to a height of 800 miles? Wow, they're mixing their units like crazy. Here, your D here is going to be 800 miles. Now, why I say they're mixing, metric ton is a SI unit, miles is a U.S. customary unit. Okay. Now, they also say use the radius of the Earth, which I'm called R sub E. Radius of the Earth is 4,000 miles. That's not exact, but it's a good approximation. For some reason, the M's not writing too well. Do not consider the effect of air resistance or the weight of the propellant. We're going just to ignore that. Okay. Now it says because the weight of the body varies inversely as the square of the distance from the center of the Earth, the force exerted by gravity is then this is the force exerted by gravity. I'm going to call this F sub. This is so aggravating. Why that does that? I've got to be able to find out some way to. There, it did it again. There's something about the sensitivity of this thing. If you hold it there more than a fraction of a second, it then changes. I don't know why. So this is your force due to gravity, which is your F sub X. Okay, this is the variable force, and that is C over X squared. Now they just throw in a C there. That time I just barely got the squared written. Okay, where C is a constant of proportionality. Now, because the module weighs 15 metric tons on the surface of the Earth, and the radius of the Earth is approximately 4,000 meters, you have, plugging this information here, this is the weight on the surface, this is the radius on the surface, you have the F of x, I'll just write it that way, I don't like to write my g's anymore, is equal to c over x squared, but we're going to have this F to be 15 metric tons. And again, that's probably not the right unit for that, is equal to C, that's your proportionality constant. What we were calling Hooke's constant before, that's the C here. And here comes somebody, I can't read who it is. Can anyone see who's trying to get in? Kyle is here, good deal. Okay. I won't say that too loud after he's in here, but okay. Kyle is here. There we have Kyle here. Okay. Oh, I forgot to let him in. Maybe I should do that. Okay. I got so excited to put him on the roll book, I forgot to let him in the class. So 15 metric ton is equal to C divided by 4,000 miles squared. That's a huge number. 4,000 miles. They are mixing the units like crazy here. Squared. Okay. So what's your C? C is equal to 15 times, this will be 1, 6 followed by 6 zeros, 16 million. It is a huge constant, okay? And that will be in tons per square miles, okay? Which is a weird unit, okay? Yep, okay. So it's 15. I have to get my calculator back. All right. 15 times 16 million equal 240 million. Okay, that is your C. Nice little round number, right? And by the way, Cal, I hope you're in by now. We're in Chapter 7, Application of Integration, Section 7.5, Work. We're in the portion on variable work, and we're doing example 3, top of page 488. Okay, and we're at the point of calculating the constant, proportionality constant, which I can't get my pen to show up here, and I don't know why. Oh, there you are. Okay, there you are. So this C is 240 million. And to keep from having to write all those zeros, I'm going to put it capital M. Okay. Now the units here are metric ton, which this is not the correct abbreviation for it, per square mile. Okay. There's something wrong with this picture. And the problem is, no, it's not. That constant proportionality, those are not the right units for it, okay? Because, well, we won't get into that. So let's forget the units for now. That's what we're going to be using. 2400, forget your units. Otherwise, I think that'll just be confusing. We'll go back and put them in at the end if I can find where the pen went to. There it is. Okay. So we'll just sort of wipe out those units for now. Okay. 240 million. Okay. So our increment of work, your delta W, I'm doing it the way the book does. I usually don't put this many steps in here. That would be the force, which is your weight. This thing here. This is your f of x here, okay? So that would be c over x squared, okay, where we'll put in the c. I'm just going to use it now, times your delta x, okay? That's basically what they're doing. So putting the numbers in there, this will be 240 million, and for right now I'm just going to put capital M for million, over x squared times dx, or delta x, I guess I should still say. Okay, and then if we're going to integrate that, the work would then be the integral from, and it says to raise it, I've lost my problem, 800 miles. So you're going from 4,000 miles, that's the from the surface of the earth, to 4,800 miles. Okay, and then we'll do this, and let's get our 240 million out front, and then you have dx, well, let's just write it this way, x to the minus 2. That's easier to integrate. X to the minus 2 dx. Now, here's the 240 million. I'm going to abbreviate it like that. Okay. And what is the antiderivative of x to the minus 2 dx? Anyone do that for me? Again, increase your exponent by 1. Negative 2 plus 1 would be negative 1, so it's x to the minus 1 over a minus 1, which I'm just going to put the minus out in front, okay? Which, that's the same as 1 over x. X of minus 1 is 1 over x, minus out front, evaluated from 4,000, yuck, to 4,800. Some pretty big numbers here, but I think we can live with them. Okay, so that would be 240 million, again I'll abbreviate for now, times minus 1 over 4,800 plus, normally it would be a minus because the minus there, it makes it a plus, 1 over 4,000. Okay. Now, there is a fairly easy way to do this on your calculator. Hopefully y'all are already familiar with this kind of stuff, but in case you're not, my calculator is not logging on. Okay, it finally did. Okay, there's my 240 million. It's still on the screen, so I'm going to turn it this way. And I'm going to do times, I'm going to open a parentheses, and then do 4,800, 4800. I'm going to change the sign of that and make it a negative, and then do the 1 over x key, okay? And then add to that 4,000 times the 1, hit the 1 over x key, close your parentheses, hit equal, and I get 10,000 joules, okay? I had to think of my units there. No, not joules, foot-pounds, 10,000 foot-pounds. This is the first time they no, oh my goodness. No, not foot-pounds, miles tons, which is a strange unit, but because they're using the Hooke's law constant in metric ton per mile, okay, then, and multiplying it through our thing here, that came up with miles tons, okay, and then they took that using a conversion. Now, do y'all really feel like you need to go through all these conversions? If it's a physics class, for certain you would need to. How do you feel about it now? Do you want to see all these done? I'll be glad to show them to you. But if you're not really interested, it's just using class time. So what you think? You want to say again? No? All right, thank you. You can look in the book and they give you these. It's 10,000 mile ton. That's what I got on my screen. 10,000 mile ton. Um, your conversion factor there, you put miles in the denominator, 5,220 feet in the numerator, and then a metric ton. You'll put 1 metric ton in the denominator, and in the numerator you would have 2,205 pounds there. And when you multiply all those up, you get an enormous number, 1.164 times 10 to the 11th foot-pounds. And then if you want to convert that to joules, it's an even bigger number because a foot-pound is considerably more than a joule. 1 foot-pound is 1.355582 joules. So you do another conversion there and you get that many joules. Okay, that's enormous. Okay, but thanks for saying no. Okay, so I'm going to go on and close that out, and let's move on to, we've already done the next couple of slides here. So let's go back to this current slide, and we already did example 2, and we did this slide earlier. So here we're ready for example 4. This is the top of page 489. A spherical tank of radius 8 feet is half full of oil that weighs 50 pounds per cubic foot. Okay? Find the work required to pump all of the oil out through a hole at the top of the tank. Okay? Now, I'm going to let them show as much of the drawings as possible. So let's see if they can draw. Ah, there it is. Consider oil to be subdivided into discs. Remember our disc method? Into discs of thickness delta Y. Okay? And radius X. Now that radius is going to vary if you're near the equator, you might say, of that tank. It's going to be a fixed amount, but as you pump it out, the radius is getting smaller and smaller and smaller. So that radius is going to be X as shown here. Okay? Now, where you're having to, here's the disc. They're showing one disc down here. Okay? Now, what they've done, they set this tank on the XY axis. Okay? On the XY plane down here. No, I'm sorry. On the plane where the x-axis is, okay? And then they're having the y-axis go up this way. So you're going from 0 is the bottom of the tank to 8 is the middle point of the tank, up to 16 is the top of the tank, okay? So that's the way they've set it up, okay? Now your y value is this thickness of oil below your disc. That's your y, because y is 0 down here and it goes up to 8 right here. Okay, so you're varying y from 0 to 8, and since you're going to have thicknesses of delta y, that's going to turn into a dy, so that's going to be your limits of integration, 0 to 8. Okay, now how much are you pumping? How far are you pumping? Well, how far you're pumping is 16, because you have to pump it up to the top of the hole, which is the top of the tank, which is 16 feet up there, but you're only having to pump it up from wherever you started at y. So 16 minus y is how far you pumped it. So there's that dimension. Okay, that's your distance. Now you need to figure out the volume, basically, of that that disc of oil. Okay, and what you're told is the what basically is the density. Now it says my internet connection is unstable, so I'm going to quit talking for a minute. Okay, when I said that, did it break up any? Yay or nay? Were any of you able to continue hearing me? Can you hear me now? I feel like a Sprint commercial. Oh, you can. Okay. Did I break up in the middle there? Yes. Okay. Well, hopefully it's back now. Okay. So your density is 50 pounds per cubic feet, we have to figure out what is the volume of that disk of oil. We know the thickness of that is delta Y. We know the area of that is, the way they set it up now, so the y-axis goes through here, the radius of this disk is your x. That's all, x. Okay. Now, at some point, we're going to have to get this x expressed in terms of y, because you can't have two variables, not with the skills we have now, in your integral. You're going to have two, but one. But that's not going to be too bad either, because you see, if you did a little triangle here, this y here, that x here, and that proportion, x is to y, is similar to 8 is to, well, that's not quite right. I was going to say 8 is 8, but that isn't quite going to be what we need it to be. Let's picture, let's see if they're going to do it on the next slide so I don't have to draw it. Okay. They're not going to draw it, are they? Okay. Man, what a pain. Nope, they didn't. Okay. So they're skipping one of the more complicated parts of the problem. Okay. Let me get you to where it is. Okay. That volume right there. That's the part that we're having to calculate. And okay, this is the tough part right here. Okay, we know it's 50 pounds per cubic feet per the volume of that disk. So what is the volume of the disk? Here is where they tell you. The volume of the disk is pi x squared times your delta y. Okay, now they still haven't gotten the x in terms of y, but that's certainly a start. Let's go back here and look, and the thickness of that is delta y, the radius is x, pi r squared, or pi x squared, is the radius. I was trying to get that changed for you now. They're not going to do it yet. Times delta y, that's the volume. Okay? But we still got to get that. Now, here's where they get it. For a circle of radius 8, this is the one up there at the center, where you have a circle of radius 8, the center at 0, 8, you have x squared plus y minus 8, okay, squared is equal to 8 squared. Okay, now you might say, what? Okay, let's go back here. This is what I was trying to show you before, and they're doing a terrible job showing it. Let's say we're up here on the surface here, and there your radius is x. Okay, so x squared plus your y squared. Well, your y squared there is, they're using the 16 minus y, which I guess is what you're using for your depth. So that squared, that's equal to 8 squared, because here at this place here, you're exactly 8 squared. So this is your ratio that I was trying to tell you about. I said it was sort of messy. X squared plus y minus 8 squared. Now that's not the same one they were using. Y minus 8 squared. Let's go back here. Yeah. This is your y. So your x squared here plus, and that's where it's coming from, y minus 8 squared. Okay. Up here is the 8. Y is equal to 8. And down here, this distance here is y minus 8. Not the same as this one. I'm sorry. 8 minus y, isn't it? No, y minus 8. Well, it's not going to make any difference because you're squaring it. That's equal to 8 squared. That's the part they're just sort of glossing over. But that is indeed, to me, one of the keys to the problem here. Okay, so x squared is equal to 16 minus 16y minus y squared. And see, they skip steps like crazy here. And this sort of aggravates me. I think I'll have to go and do that one because they skip so many steps there. So let's go back to the whiteboard and let's clear this out of the way because that's the previous problem. Okay, now what they just had there, that's their that's sort of the key to the problem here, and they just skip right on over it. That I wish I can't draw this well. I'm going to try to. So let's say that is, ooh, that didn't come out well, did it? Okay, that's your hemisphere, if you can imagine that. Okay, where x is measured from here to here. So your radius here, right here, say, is x. Okay, now your height here is y, but what they're using is they're going from here, okay, and this is your 8. This is your y down here. So this right in here is 8 minus y. But because we're squaring it, you can call it y minus 8. It doesn't matter. It's the same distance there. So that's why they're getting that the x squared plus y minus 8 squared is equal to 64. 8 squared. Okay, now that's basically your Pythagorean theorem there. Okay, and they're talking about it when you're up here at this point here. Okay, but I'm just going to work this out for you. So it'll be x squared plus, well, yeah, let me do it, plus y squared minus 16y, this is just completing the square, plus 64. And that's equal to 64, 8 squared. Okay? When you subtract this from both sides, that gives you x squared is equal to the 64 subtract away, and then you wind up with 16y minus y squared. That's where they get the x squared is equal to that. So now we can express this x, but we don't really even have it as x. We're always squaring that because it's pi r squared, pi x squared. So there's your x squared. All right, so that's where they got that. Okay, so let's just go back to the formula here. I mean, I don't want to take this much time with this problem because we really need to move on. Let's go back to our current slide. Okay, so that's where they got this part. X squared is equal to that. Now up here we found out that the x squared, the 50 is your density, pounds per cubic foot. I think these were in feet. Pi r squared is your area in cubic feet times your thickness in feet, area in square feet, times your thickness in feet. Instead of this x squared, they're putting the 16y minus y squared. So your delta F, your incremental force, is this 50 here, See, this is what this was. 50 times pi. There's your x squared. They've just written this down again. And plugging this x squared in for that, here's what you get. 50 pi times, pull the pi out with the 50. Those are all constants. Here's your x squared, 16y minus y squared, then times your delta y. That's what you're going to integrate. Okay? Now, it says, note that a disk y feet from the bottom of the tank must be moved. That volume that's from here has to be moved, and that's where our 16 minus y comes from. That's how far you move it. Everything's in terms of y, so this now, the increment of work, delta W, is equal to the force increment, which we were just dealing with, times the distance, which is still a function of y, okay? Okay, times your, and this delta F has in it your delta y, so that's where the delta y is coming from. So plugging that in, your delta X is your 50 pi times the 16 y minus y squared. Now I would go on and pull this delta y out to here, but they're leaving it there for now, times your 16 minus y. Okay? Now, what they've done here is multiplied this binomial times that binomial. And they skipped all the work of that, and here comes somebody. Anyone see who this was? Oh, Daniel Thaxton. Okay, let me get him in and also mark him present. Okay. Okay, I don't know if you can hear me yet, Daniel, but welcome. We're in Chapter 7, Applications of Integration, Section 7.5, Work, and we're in the part on variable work, and we're doing a variable work problem where your force is the variable part and your distance is also a variable part, but not as variable as the other. And we got to this point, and maybe y'all can do this on your own, but let me just go on and do it for you just in case. We're going to do that calculation they just did. So I'm going to clear what I've drawn here and rewrite this. Here is where we had it left at. We had that the delta W, the increment of work, was equal to the delta F, which is 50 pi. The 50 is your density, pi is from your area, and the x squared is your 16 y minus y squared. Now that's yet another whole problem that we already talked about, times your delta y, which I would just as soon not put here, but because the book did I would, and then you're multiplying that by the height that it was raised, and that was your 16 minus y. Okay, so what we're going to do now is the 50 pi is just a constant, so let's keep that on the outside. Okay, now the delta y, we're going to move over here to a delta y. What we're doing now is multiplying these two binomials together. So 16y times 16 is 256y. Okay, and then this one times that one, the outer terms are minus 16y squared, and this will be another minus 16y squared, and then finally plus a y cubed. I didn't leave enough room, did I? That's what we're integrating. So your total work is the integral, 50 pi out front because that's a constant. Okay, now where are we going from? Y is our variable. We're going from, basically, this is another part. We're going from 8 down to 0. Okay, now that's rather strange. The book writes it 0 to 8. In reality, you're really doing 8 to 0, but we'll do the way the book did, 0 to 8, and okay, and then this is your integrand. That would be 256 y minus 32 y squared plus y cubed, and then it's the dy. The delta y becomes a dy. Okay, this is your 50 pi times, okay, antiderivative of 256y, 128 y squared. I've already divided by 2. That's where that went. Minus, this will be a 3, not going to be able to divide by that, 32 y cubed over 3 plus y to the 4th over 4, evaluated between 0 and 8. Okay. I'm not about to do anything but use my calculator here. Hopefully you got yours. Okay. Clear that last one out of the way. I'm going to have to go sideways here so I can use the pi. 50 times pi times, open parentheses here, okay, and then you have 128 times 64, which is 8 squared, that's 64, minus, and I can't do this one in my head, so that's going to be 32 times 8 cubed. This is tough on the telephone. Divided by 3 plus 8 raised to the 4th power. Oh boy, yeah. Divided by 4, close parentheses, equal, oh my word, let's see what we got. Yeah, 589,782 rounded up foot-pounds, because you're measuring everything in feet and masses in pounds. Remember, our density was pounds per cubic foot. So that's what we got. Now that was more a convoluted exercise in geometry and arithmetic than it really was too much calculus. This was the only calculus part right here, doing the integral that you had to get from up here, which was the geometry part, to get to this integral, integrate that. That's the easy part, and then doing the calculations was the mathematical part. 589,782 foot-pounds. And the U.S. customary unit for work is foot-pounds, not joules. Okay. And that's what we got. And really convoluted, and I'm not at all pleased with their rendition of where they came up with that that key thing that x squared plus y minus 8 squared is equal to 8 squared. It's true, but they didn't show it well in their illustration at all. Okay, so I'm going to get out of this and let's go to the next problem. Oh, wait. I I keep forgetting. This one was on the slide set, wasn't it? So let's see if they do any. No, we know they don't because we've been there before. I was looking for it before. Okay. See, they go from here to here without telling you beans about how they came up with this. Okay. They don't show you in the picture anywhere. It's right, but we just don't have time to do it any more of it. So that's what we evaluated. Why in the world they put the 50 pi inside, didn't take it outside, I don't know. But anyway, when they do, there they took it on the outside. And there's your integration. That's the easy part, isn't it? 256 y squared over 2, well, 256 divided by 2 is 128 y squared, minus 32 over 3 y cubed, plus y fourth over 4. Evaluated, from 8 to 0, and there you have, I did it on a calculator rather than carrying all that around, but it is doable that way. And that was about 589,782 foot-pounds. Now, number one, this is not a physics class, okay? Significant digits are out the window here. Nothing in your problem gave you any more than 1 or 2 significant digits. Here they give you 6 in the answer as if you're precise to that level. You're not. You know you're not. But that's okay. This is math class. Okay. Now, they say to estimate the reasonableness of this answer, let's just consider the weight of the oil in the tank as 1/2 the volume times the density. Well, the volume of the tank is 4/3 pi times 8 cubed. Okay? Now, the density is 50 pounds per cubic feet. 1/2 is because you only got half a tank full. Okay? When you plug that in, goodness, my nose is itching. Whoa! What happened to my slide? Yeah, when you plug that in, and you can do the math of it, I'm just not going to take the time to do it. They say you get about 53,000 pounds, 54,000 almost. Lifting the entire half tank of oil would be the work of, if that was just lifting it up, not doing it in increments, then that would be that much raised 8 feet. Okay. Well, 8 feet wouldn't get you, but the top part to the top, you still have more to do because the oil is actually lifted between 8 and 16 feet. The biggest part at 8, but then the smaller part at 16. Seems reasonable that something greater than this would be your answer, and we got something greater than that. Again, that's just reasonableness. It's not a proof. Okay. Now, that was example 4. They don't do example 5 or 6. Okay. Now, what you say? Want to see them, or you rather not? Anybody? I'm happy to do them if you want to see these. Let me know something. You want to see them? I'm not hearing any answer whatsoever. 5 and 6 are not shown on the slideshow. You want me to do them on the whiteboard? Yes? Say again? Yes, I thought so. I would have said yes myself, but I didn't want to force it on you if you didn't want to. All right, so let's clear the whiteboard and let's do example 5 at the top of page 490. Now, what I'm going to do here to keep from having to draw it, I'm going to show you the picture. Okay? Here's what you have. You have this front end loader picking up a chain, and you're figuring how much work it took for it to lift the chain. Okay? Now that first little link to go a little bit of distance is not going to take very much. But then the next link up, you got that first link plus the weight of the next link. So the further you lift it, the more you're lifting. So that's a variable work problem. Okay, so that's the setup. Now, let me get my Wacom back in place so I can do it. I couldn't hold it and doing that. So here we have what we have is a 20-foot chain. So, well, it won't work if I have my pen on backwards. Okay, we have our total length. I'm just going to call it capital L. Is going to be 20 feet. We'll come and put that into play later. Okay, and it weighs 5 pounds for a foot. So I'm going to call this a length density. Okay, that's 5 pounds per foot. Now this isn't anything you've seen before, but we'll see how to handle this. Okay, it's lying coiled on the ground. It says how much work. So what we're looking for is work, which is what we've been doing here. How much work is it going to take required to raise one end of the chain to a height of 20 feet? So you want it all the way off the ground. So you want it, that last link is just touching the ground. Okay, so it's fully extended. It's shown in the figure, the second figure I showed. Okay, so let's just imagine that the chain is divided into small sections. Let's think basically almost links. Link, L-I-N-K, each of length of delta W. So delta Y. Okay, that's going to be our incremental length. The delta Y is the incremental length. Okay, so everything's going to be measured in terms of that. Y is going to go from 0 to 20. So that's where the 20 comes into place. You're lifting everything like that, 0 to 20. Okay, all right. So your delta F, that's what we're going to do first. We're going to break the force down into increments. Okay, the delta F, that is your weight. Okay, and that delta F is going to be, well, certainly you got to have the weight in there, so that's where your density comes from. 5 pounds per foot. Okay, so that's your density part. Okay, now what you have here now is times the length that you raised it. Now they didn't show in the figure, but you're going up Y. Remember your delta Y, so you're raising it. How far are you raising it? You're raising it Y feet. Y is going from 0 to 20. Okay, so there is your that's your delta Y. Okay, you're raising it only this delta Y, sorry, not the total length. Okay, so they're taking it one step at a time. So the delta F is 5 delta Y. Now I'm going to leave off the units here like they do and just make this 5 delta Y. That is the incremental force for every length I pick it up. Okay, now because the typical section initially on the ground is raised to a height of Y. Okay, so that's how high we're lifting it at any moment. Okay, so the delta work then, there it is, delta W would be this force, 5 delta Y, times how far did you lift it. That's where the Y was coming in. You lift it 5Y. So that's your delta W. Okay, and that's what we're integrating. So your total W is going to be the integral from 0 to 20 of 5y dy. Okay, now the hard part is getting that set up. The easy part is the calculus. Okay, what is the well, let's pull the 5 on the outside. Okay, antiderivative of y dy would be y squared over 2. Well, let's take the y over 2 outside too. Y squared evaluated from 0 to 20. Okay, so this will be 5 halves times 400. 20 squared is 400, 0 squared is nothing. 2 will go into 400 200 times. So this looks right around 1,000. 1,000, and we were measuring in foot-pounds, so foot-pounds. Okay, and that's what they got. Okay, now in the next example, you'll consider a piston of radius r in a cylinder casing. And again, I don't want to have to draw this, so I'm going to hold it up for you so you can see it. Okay, here's what we got. For any of you mechanical engineers, you may run into this a lot. Here you have a piston inside the cylinder casing, and as the rotor turns here on that arm, you're pushing the piston and compressing the gas. This is what your car does every time it makes one turn of the engine, which is a lot of times. Compressing the gas. That's what we're dealing with here. Here is the variable, I guess it's X, I can't read it here, and that shows the length that hasn't been compressed. Okay, so that's the setup here. In the next example, you'll consider a piston of radius r in a cylindrical casing, shown in that figure I just showed you. As the gas in the okay, they've got it going the other way. They've now ignited the gas and it's pushing. So I'm sorry, you weren't compressing. The gas is ignited and it's pushing the well, basically, ultimately a flywheel. Turning the cylinder. Okay, turning the crankshaft. That's the word I was trying to think. The crankshaft. Okay. As the gas in the cylinder expands, the piston moves, work is done. If P is the pressure of the gas, so I'm going to do it here because I'm going to have to go to a clean slide in a minute. P is pressure. This has nothing to do with this problem now. This is pressure. Okay, that stands for pressure of the gas in pounds per square foot. And pressure is force per unit area, so that's a reasonable pressure measurement. Against the pressure, against the piston head, that's the pressure against the piston head, volume of that gas as it's expanding, V represents the volume of the gas, so I'm just going to write volume of the gas as it's expanding. Okay, then the work increment involved in moving the piston x feet, delta x feet. So the piston started here. Here is, ooh, that's just ugly. Okay, there's your cylinder. Okay, it started, and this is your X here, and you're pressing the gas here. Okay, it's increasing X going in this direction. Okay, so as you're increasing that, the delta W, the work done by that doing, is force times the incremental distance. So now we're going back to incremental distance, dx. Okay, but you got to figure out what that force is. Okay, they use capital F here, so I will too. Okay, now what's the force? Force is pressure times volume. Okay, now how do you get that? Well, pressure pounds per square foot, volume is in cubic feet, so that would give you foot pounds. Well, foot pounds is a good measure of work. Okay, so the delta W would be that, the pressure times the volume. But now remember, the volume is varying. That's what's changing. Now the pi r squared, that's the radius here, that's not changing at all. That's fixed, if I can get this. The area of this is pi r squared. They didn't tell us what the r was, but that's pi r squared. That's not a variable. The increment here is in your delta x. Okay, as you compress the gas a little bit more, that's definitely a variable force. So that's your delta F. The force is what you're put on it, which is also variable, by the way. Okay, but we're going to calculate it every time. And that force is, as I was saying here, it's, okay, as I almost got it set. The pressure times the volume will give you foot pounds, I mean pounds per foot. Okay, if you multiply pressure times volume, multiply that though by your delta x, okay, and that gives you pounds. So this is your force. It's the pressure times volume times your delta x. That's your force, and your distance is x. Okay, no, I'm sorry, they've left off a unit here somewhere. Okay, I am not sure I'm agreeing with this too much. If pressure is in pounds per square foot, that's what I said, multiply that by a volume. Okay, that's where the thing is. The volume is this. The volume increment though is your area times your delta x. So the volume is is pi r squared delta x. Okay, that's your delta v. Delta v. Okay. They're not printing this too well. Okay. And then they're making all sorts of assumptions here, and here's what they get down to. Okay, that the work done, and this is basically what it gets down to in real life too. The work done is your integral from your V0 initial volume to your final volume. Okay, now they put V1. I'm not sure why they do V1. I'll put V final. Okay, and then you have a proportionality constant we haven't even brought up yet over V times your dV. Now they jumped a bunch of rabbits there all at once. Okay, actually the line before that one was this one, that the work was same thing, V0, and they call it V1, so I'll put V1 too. I'll put VF before because I didn't pay attention to what they were doing. And this is what they call the pressure times the increment of volume. Now that does make sense. The work is pressure times volume. See, earlier they said the force was the pressure times the volume. That's where I was getting uh, you know, that's what was bugging me like crazy. Okay. Uh, Now, I guess I just misread what they were saying, but that is correct. Work is pressure times volume, because that's what I was saying before. Pounds per square foot times a volume, cubic feet, that gives you pounds, foot pounds, okay, and that is your measure of work. I was thinking they were calling that force. I said, no, that's not right, okay. So, yeah, I guess I just misread what they were saying. So anyway, that's the setup that they're talking about here. And then they just coming up with this formula is rather bizarre. They haven't even told you what the K is yet, but let's clear that out of the way and do example 6. A quantity of gas with an initial volume of 1 cubic feet, so that's what they called the V0, is 1 cubic foot. And we probably won't need the units, but I'm going to write them down now to begin with. And a pressure of 500 pounds per square foot. So this is, the gas is, now here's the problem. That's also an initial pressure. Now they don't make a deal about that, but that is an initial pressure, okay? And that's 500 pounds per square foot. Because you know that's got to change too. Pounds per square foot. Okay. Expands to a volume of 2 meters. Okay. So your V1 is what they're calling it, is 2 cubic feet. Okay. Find the work done by the gas. Assume that the pressure is inversely proportional to the volume. And that's where the K over V came from. Okay. So that's their other assumption, that the pressure is equal to, is inversely proportional to the volume. So this gets you out of the pressure realm into the volume realm. Okay, that's what you're going to be measuring here. Okay, now, because you know this first thing, and you know the initial volume is 1 cubic foot, then you know that K is equal to 500 times 1. Okay, so that would be 500, that's pounds per square foot, times 1 cubic foot, that would be foot pounds. Okay, that's your K, which is interesting because, and they don't put the units down with it, they just say that. Okay, they just put 500. So the work done by the gas then, by the formula they just came up with, is work is equal to the integral from V0, 1 cubic foot, to 2 cubic feet of this constant 500, which I just assume right outside here, and that would be foot pounds times dV over V. And you see your units make sense now, because this is in foot pounds, these are in cubic feet, and your V is cubic feet, this is cubic feet. So the units inside the integral basically cancel out. So the calculus is the easy part. Getting up to this is the hard part. So this is your 500 foot pounds, I'm not going to write the units here, times the integral, I'm going to rewrite it 1 to 2, of V to the minus 1 dV. That just makes it easier to integrate. 500. Now, what's the antiderivative? No, it isn't. I should have left it like this. Sorry. Ignore this here. Okay. What is the antiderivative of dv over v? Somebody answer me. Natural log of v. Evaluated from 1 to 2. Okay. So this will be 500 times log 2 minus log 1. Huh. What is log 1? Anyone know? 0. So there's your answer, and this is in foot-pounds. Log 2 has no units to it, and if you have your calculator, I'm going to see that doesn't quite look like it works, but let me get to my calculator and see if it works. I have to turn it sideways to get the log to come up. Not coming up, and I'm about to drop my pen. Okay, I can't get the calculator to go sideways. There we go. It did. Okay. So that's 500 times the log of 2. So on this calculator, I have to enter the 2 first, then do the ln key. Yep, that's going to work. 346.6, or I would just say 347. Okay, and that's, you don't have enough units to carry around that much. That's about 347 foot-pounds. I think I started to write foot-pounds here and didn't. Okay. All right, and that's what the book got. Sorry about that. They skipped tons of steps in their setups, which is probably, I found irritating. I had an old gentleman in the class a couple of terms ago who was, I think, 78 years old, and he just hated this book for all the steps they skipped, because the book that both of us had used in college, he had an earlier edition than mine, was they worked out every step, and he loved that book, but they don't publish it anymore. Okay, but anyway, homework exercises 7.5, do either 5 or 7. They're both at Calc Chat. 7's at Calc View. Any of the odds 9 through 13, they're all at Calc Chat. Number 11's at Calc View. Then do any of the odds 15 through 19, they're all at Calc Chat. 20 you can think about doing. It should be at Calc Chat. 20, wait, I'm sorry. Yeah, 19 should be at Calc Chat. Wait, either 19 or 21. They're both pumping water. Actually, any of the odds 19 through 25. They're all pumping water, just different geometries you're pumping from. So do any of those. Then do 27 is pumping gasoline, which slightly differently, but not too bad. And then winding a chain as opposed to lifting a chain. This was 29 or 31. They're both at Calc Chat. 29 is at Calc View. 33 should be at Calc Chat. That's lifting a chain. And then 35 is exploring a concept. You can think about doing that one if you would like. It's up to you. There's 37's Newton's Law of Universal Gravitation. 39 is electric force, Coulomb's law. You can look at 41 if you'd like. That's up to you. Here's another law, Boyle's law. 43 is both at Calc Chat or Calc View. And then there's a hydraulic press problem, either 45 or 47, both at Calc Chat. 49 is a modeling problem. They say you might need graphing calculator or graphing utility, so that's up to you whether you want to tackle that one. And then there's a sort of an interesting little blurb. You don't have to do it, but if you want to read it, the Pyramid at Khufu, known as the Great Pyramid of Giza, the oldest of the seven wonders of the ancient world, and it's the tallest of the three Giza pyramids. It talks about how much work it took to build that. Interesting little problem, not anything we're going to do in class. Thank you. Okay, so let's move on to 7.6. Now, I had this open, and oh, that may be it right there. Let's see. No, it isn't. I thought, no, that's still 7.5. I don't know why they opened 7.5 twice and didn't open 7.6. So I guess I'm going to have to pull out for just a moment. Okay, I think what I'll do here, okay, I'll click on that. Okay, now I've exited that for just a moment. I'll get right back in as soon as I can. Let me pull up 7.6 again. It's in here. I pulled it up before. There's 7.6. Okay. Okay, let's go back to, well, I can't get back to Zoom. There we go. We're already in progress. I don't need that slide. Ah, here we go. Well, still not showing up. How do I get back to Zoom? Well, let's try it this way. Return the meeting, that's it. Sorry, it was up there before. Okay, now we'll do the screenshot to 7.6. Okay, we're back now. Y'all can see that, right? But at this point, I have to, yuck. This pen tries every way it can to fall. Okay, I'm going to scoot some things around here. Okay, I did it before, but then it undoes it every time I make a change. Okay, so here's 7.6. Let's go from current slide, if I can get it to come up. And let's see, we've been going at it for about 2 hours. We've got about an hour left, right? No, that's not, yeah, a little bit less than an hour. I'm all in favor of a bladder break. Do any of you have any objection? So let's do a pause on my recording right here. Now remind me to, all right, for any of you who are watching me hobble out of the room, that's the added benefit of my taking a break, because I have a knee that when I sit in one position too long, it stiffens up on me like crazy, and that's what you are seeing me trying to work it out. So that's an added advantage of having a little break there. So thank you. Sorry I had to take it, but all right, we're moving. Any questions on 7.5 before we leave it? All right, 7.6 is moments, centers of mass, and centroids. Okay, are any of you prospective mechanical engineers? Any of you? Okay, if you were, this is certainly going to be something big for you. Probably civil also will have this to contend with a lot, but frankly I think all, at least back when I was in college, that was a long time ago, all engineers had to take statics and dynamics, and if you got that, you're looking forward to that. This is all over the place in that, whether you're going to be using it or not, you're going to have to deal with it there. So anyway, This is Applications of Integration, Chapter 7, and it won't advance until I touch the screen. Okay, and 7.6 is Moments, Centers of Mass, and Centroids. Now, some books really drag this out. This book moves this along pretty well, so we're going to try to go with the book. Okay, though it does have a lot of objectives here. Understand the definition of mass. That sounds pretty straightforward. Find the center of mass of a one-dimensional system. That's pretty straightforward. Find the center of mass of a two-dimensional system. Not that much worse. And then find the center of mass of a planar lamina, which is a pretty simple, fairly simple concept as well. And then theorem of Pappus, really simple, to find the volume of solid of revolution. Okay, so let's start with mass. Several important applications of integration are related to mass. Okay, mass is a measure of the body's resistance to changes in motion. Now that's an odd way to think of it, but it certainly is true. Very physics oriented. What a body's resistance to changes of motion is its inertia. Mass is a measure of a body's inertia. Think of this, a ping pong ball. Not hard at all to bop that around and it changes motion. Very little resistance, very little mass. Bowling ball, on the other hand, you better get out of the way, because to change its motion, it's going to take some pain. Okay, it takes a lot more force to change the motion of a bowling ball than it would a ping pong ball. Now, mass is independent of the particular gravitational system in which the body is located. Okay, for instance, if I have a mass, and I do here on Earth, I'd have that same mass on the moon, same mass on Mars, same mass wherever I go, anywhere, not just in the solar system, anywhere in the universe. My mass doesn't change unless I'm gaining or losing. Now, weight changes like crazy. Weight here on the surface of the Earth is too much, but it's here. But if I were to go up into a spacecraft, a few hundred or thousand miles up, I become what they call almost weightless. You're not really weightless, but you feel like you are, because you have so little weight compared to what you have on the surface of the Earth. So a very easy way to lose weight is go up into space. Now you become weightless. Your mass hasn't changed any. As soon as you come back to Earth, you got the same weight back again, but you lost weight in the meantime. So that's the difference between mass and weight. Weight depends on the gravitational system that you're either in or not in, and mass is independent of that. However, because so many applications involving mass occur on the Earth's surface, the object's mass is sometimes, they say equated with, that's not good, made equivalent to its weight. Not equal to, but equivalent to its weight. That's not technically correct if they equate it. Weight is the type of force, and as such is dependent on gravity, but if you're anywhere on the surface of the Earth, gravity is constant. Okay, so force and mass are related by this equation. Force is equal to mass times acceleration. That's basically Newton's second law. Force equal mass times acceleration. Okay. The table below lists some commonly used measures of mass and force, which is really unusual for a math book, but it does it, together with their conversion factors. Okay? The U.S. system of measurement, we hardly ever use mass because its unit is a slug. We don't even use that as a unit, but that's what the unit of mass is in the U.S. customary system. Okay, there's not even an abbreviation for it. If you were trying to do it, you'd have to spell it out. Just like here, they spelled out slug foot per second squared. Notice they abbreviated feet, they abbreviated second. Pound would be lb. Slug, there is no abbreviation. No one uses it. They don't even bother with an abbreviation for it. Now the SI system, that's what they're calling international. SI system, the measure of mass is kilogram. Now the measure of force is a Newton, which is a kilogram meter per second squared. Notice mass times acceleration. Mass times acceleration. That's what Newton's second law is. In the CGS system, which is something they used to use a lot more, they don't much anymore, but the measure of mass is the gram, not the kilogram. This is for small units. Gram, and then the measure of force is a dyne, which is a gram centimeter per second squared. See, centimeter, gram. SI is meter, kilogram. It's sometimes called the MKS system. This is CGS system, centimeter gram system. So that would be a gram centimeter per second squared. Second doesn't change, it's the same. Okay? You don't need to know those, but there they are. The conversions here, pounds are equivalent to newtons. Okay? And this is the conversion. 1 pound is way heavier than a newton. It takes almost 4.5 newtons to make 1 pound, 4.44822 newtons to make a pound, or just barely more than a fifth of a pound, between a fifth and a quarter of a pound, makes a newton, 0.22481 pounds. A dyne, though, is way smaller because the difference between a dyne and a newton is you got a power of 3 here and another power of 2 there. So it's a power of 10 to the 5th. Okay, 10 to the 5th. And that's why your decimal moved 1, 2, 3, 4, 5. Oh, yeah, 1, 2, 3, 4, 5 places. Because that decimal was there and this one's here. 5 places, 10 to the 5th. And like it said here, this is exactly 1, 2, 3, 4, 5 newtons. Okay, 5 places to get to a newton. A dyne is 10 to the minus 5 newtons, or 1 newton is 10 to the 5th dynes. Slugs, no one uses them at all, but if you were to use them, slug is a pretty good sized mass because a kilogram is a pretty good sized mass, and a kilogram is more than 14.5 slugs. Okay, I'm sorry, a slug is more than 14.5 kilograms. A kilogram is less than, or a little bit greater than, a 20th of a slug. Okay, a gram is, again, there's a 1, 2, 3, 4. Let's see. No, here between gram and kilogram, only 3 decimal places. So 1, 2, 3, and there you have your 0.06 and your 0.06 here too. A foot is less than a third of a meter. Okay, 0.30480 meters. That would be your length measure between here and here. Okay. Interesting, the book does that. Most physics books don't even give you a table like that anymore. So here's example 1, no calculus involved. Find the mass in slugs, why would anyone do that, of an object whose weight at sea level is 1 pound. Well, let's go to our whiteboard and do that. Okay. Well, I went to the, oh, I thought I clicked on it. It didn't come up. Now I got to move this out of the way. Hang tight. I'll get with you in a minute. Okay, also, no, that's already moved. Okay, so let's clear that last problem out. And here we have example 1. Find the mass in slugs. So what we're looking for, if I turn my pen over, okay, the mass in slugs, okay, and we know this is the unknown here, okay, and we know that force is equal to mass times acceleration, okay, and they give us, now this is the acceleration due to gravity, so let me change that to a g, okay, and they give you the force, which is the weight, which is 1 pound, is equal to the mass, that's what we're looking for, times the acceleration due to gravity. Now, the acceleration due to gravity is 32, or it's approximately 32 feet per second squared. Now I don't remember they gave you that before. So to get this, you take 1 pound, divide it by 32 feet per second squared, and that gives you how many slugs. Okay, that's pretty straightforward calculation. Okay, takes longer to get the calculator open than it does to do the calculation. 1 divided by 32. 0.03125 slugs. Why in the world would you ever give a problem that no one ever uses? Okay, now this is what occasionally you will see used. Because many applications involve mass occur on the Earth's surface, that amount is often called 1 pound mass. And you'll sometimes see that abbreviated as, this would be 0.03125, and then they would call it a pound with a subscripted M. This is a pound weight. This one here, this is a pound mass. But again, that's not really all that common. Most of the time we don't even use slugs or any kind of mass unit in the U.S. customary system. Okay, so if I can get my, there it is. Okay, let's go back to the text. 7.6. Go back to current slide. Here we go. So let's see how they do it. Same way we did. Use 32 feet per second as the acceleration due to gravity in the U.S. customary system. So the mass would be force divided by the acceleration, which is exactly what we did. The force was 1 pound divided by 32 feet per second, usually abbreviated FT per S squared. Okay, that's much shorter to write. And that would be 0.03125 pound per foot per second, or slug. And then this is what I just said, because many applications involving mass occur on the Earth's surface. That is what they call a pound mass. That would be a slug. That would be 1 pound, the mass of 1 pound. Okay. So now let's talk about center of mass in a one-dimensional system. All you're doing is moving along, say, an axis, say the x-axis, just to have an axis. You'll now consider two types of moments of mass: the moment about a point and the moment about a line. To define these two moments, consider an idealized situation in which the mass is concentrated at one point. Say you have a blob here with so much mass in it. We're going to assume that mass is all at that single point, say in the center of the blob or somewhere in the blob. Okay? That's your assumption here. Idealized situation. All the mass is concentrated at one point. If x is the distance between that point mass and another point P, then the moment of that mass about that point P would then be that mass times the distance from that. Now that x, that distance you are from the mass, is called your moment arm. Okay? And the classic example of this is kids on a seesaw. Did any of you even remember playing on a seesaw? Teeter-totter? I don't know what you called it back then. Most of you, I think, have done that. Remember, if the heavy kid, and I was always the heavy kid, was on one end and the lighter kid on the other end, heavy kid sit there and the lighter kid is just hanging in space there. It's really hard. The heavy kid has to really push off the bottom, and then it goes right back, and it goes right back. That's because You have more mass a certain distance. So what you do is scoot the teeter-totter over so that the seesaw over so the light kid is further from the center, the heavy kid is closer to the center, so therefore now they can probably do it, because now you've given the light kid more of a moment. He had the same mass. Well, I'm trying to do it with my finger and I need to use my pen. I can't get it to show up. There it is. The mass is the same, but you made his distance greater, while you made the heavy kids, whose mass is more, the distance less. Now they can seesaw. Of course, the light kid goes way up higher and further, but they can do it, okay, with a little less effort. X is called the length of the moment arm, okay, and here's this example. Concept of moment can be illustrated by the seesaw. Like I said before, it's shown in this figure. The child of mass 20 kilograms sitting over here and sits to the left of the fulcrum. Here's the fulcrum, point P. The older child, heavier child, have mass of 30 kilograms, sits to the right of that P, okay? Now, if they didn't have anything to block them, all they'd have to do is this kid scoot up some and leave more distance from the end, let this kid scoot back some without having to move the teeter-totter or the seesaw. Okay, from experience you know that the seesaw will begin to rotate clockwise because the heavy kid is down there, so it's going to move in that direction if they're equidistant from the end, okay, if they're the same distance. However, all it takes is for, like I said, the heavier kid to scoot up a little bit, this one scoot back a little bit if he can, then this one has a greater riding arm than this one does, and maybe they could enjoy the seesaw. That rotation occurs because the moment produced by the child on the left is less than the moment produced by the kid on the right. The left moment was 2 times 20, which is 40 kilogram meters. The right moment was 30 times 2, which is 60 kilogram meters. To balance the seesaw, the two moments must be equal. So if the larger child moved to a position 4/3 of a meter from the fulcrum, then the seesaw would balance because each child would produce a moment of 40 kilogram meters. So this time they didn't have the light kid moving anywhere. He stayed right there. This one moved up to 4/3 of a meter. So 4 on top, 3 on the bottom, 3 goes into 30, 10 times 2 times 10 times 2. Wait, I said that wrong. 4/3. Oh, 4/3, yeah, okay. Sorry about that. This is a 4/3, so 3 will go into 30, 10 times 4 is 40. So that it would be exactly it. He wouldn't have to move up as far as the kid on the left moved back a little bit, but whatever. Now, you can introduce the coordinate line, a coordinate line, on which the origin corresponds to the fulcrum, okay? And you just let that be the origin here, where the fulcrum was, okay? Several point masses are located on the x-axis. The measure of the tendency of this system to rotate about the origin is called the moment about this point right here. Excuse me, the origin. I meant to, when we took our break, to run down and get something to drink, and I forgot to get that, so I'll try to do it at the end of class, which is coming up. What, in about, oh, and I do want to apologize and fuss at you a little bit too. For some reason I had it in my mind this class ended at 2:15 last Wednesday and got out of the class early, and not a one of you objected that I cheated you out of 10 minutes of your tuition dollar. I didn't care for that. Sorry, I don't know where my brain was, but I suddenly thought, because I have other classes that end, like tomorrow afternoon's class ends at 1:15, I just made this 2:15. we go till 2:25. So we got a little over, we got 26 minutes left. So let's go. So here we have several point masses located on the x-axis. The measure of the tendency of the system to rotate about the origin is the moment about the origin. It's defined as a sum of the end products of m1 times mi times xi. So here m1 times x1, that's the tendency to pull it this way, plus m2 times x2, that also tends to pull it this way. Those, when you set them, well, you don't know that they're equal, but then if you were doing this, well, you'd have to decide. If this is going to be negative this way, then this would be m1 times a negative number here, whatever x1 is, plus m2 times its negative number, x2, plus m3 times its positive, because that's to the right of the origin, x3, plus, and then if you had m4 here, m5, whatever, you just keep adding the masses times the displacement. That gives you moment for each mass, and the sum of all the moments for all the masses is called your the moment about the origin. Okay? Now, the moment about the origin is denoted as m sub 0, and it can be written this way. M sub 0 is m1 x1, understanding this x1 could be positive or negative. Masses are always positive, never negative. You cannot have a negative mass. You can have zero mass, but you can't have a negative mass. Displacements, however, could be negative or positive. So this could be m times x1, which x1 could be positive or negative, plus m times x2. x2 could be positive or negative. m2 is always positive. All the way up to m sub n times x sub n, where the mass is always positive. Excuse me, but the displacement could be positive or negative. If m sub 0 is equal to 0, then the system is said to be at equilibrium. All the kids are sitting on the teeter-totter and it's not going either direction. That's equilibrium. Okay. For a system that's not in equilibrium, the center of mass is defined as the point x bar. Okay, that's a bar there, at which the fulcrum could be relocated to obtain that equilibrium. If the system were translated x bar units in whichever direction to get you there, then each coordinate x of I would become x of I minus x bar, and because the moment of the translated system is 0, because that's how you define, my knee hurts, sorry. Lost where I was. Because you said this is going to be translated as 0, that if that x bar is your center of mass, you know, if that's it, then the sum of all those is going to be the m times the xi minus m sub I times xi minus x bar, then would have to be 0. So we know that the summation is I is going from 1 to n of m sub I times x sub I minus x bar. Now notice, sometimes this xi is less than x bar, so this number is going to be negative. Sometimes that xi is greater than x bar, so then this number will be positive. And if the product of that m, which is always positive, times your difference in x, which may be positive or negative, then that would be, whoa, where did that go? Why did it happen? Okay, then this would be the summation of all your xi's from 1 to n of m sub I x sub I minus m sub I times your x bar. And that's got to be 0. If that was 0, then this is also 0. And then if you solve for x bar, excuse me, that's a fixed number. Okay, whatever your that center of mass is, that's a fixed number. So you could pull that out of the summation, and then you have x bar is equal to the summation of your moments over the summation of your mass. The total moment of the system divided by the mass of the system, that gives you the center of mass of the system. So that's how we're going to use it to calculate it. Now, when all those add to zero anyway, the system's in equilibrium. Okay. So here's the definition, kind of summarizing what we were just saying. Okay. Let points M1, M2, M3 all the way up to M sub n be located at x1, x2, x3, x4 all the way up to x sub n. The moment about the origin is what we just said, m sub 1, x sub 1 plus m sub 2, x sub 2 plus m sub 3 all the way up to m sub n, x sub n. Now, if of course all the m's are positive. If all the x's are positive, then you have a pretty large moment here. But if some of those x sub i's are negative, then your moment is usually a little bit less. The center of mass, though, would then be the moment about the origin divided by the total mass. Okay, where m is equal to the summation of all the masses in the system. Okay. They skipped example 1. Okay. No, we didn't. We did example 1. This is example 2, and this is over on page 496. Find the center of mass of the linear system shown in this figure. They picked the origin there. Let's find the center of mass. Okay. Well, I don't think I can write here, so let's go to, I could write, I just can't erase. Let's go to our whiteboard and clear all this. Okay. This has that M1 at 10 is at minus 5. Now notice they don't give you any units here, and it's that x equal minus 5. So let's call that x sub 1. M2 is equal to 15 without knowing units, and its x sub I is equal to 0. It's on the origin. Okay. M sub 3 here has a mass of 5, whatever the units are, and it's x sub, this is x sub 2, this is x sub 3, and that's equal to 4 units. And m sub 4, yuck, m sub 4 is equal to 10 mass units. Okay. I'm having trouble seeing, sorry about this. X sub 4 is equal to 7. Okay. Now, I think I've got everything written right. Let's now do our calculations. It says find the center of mass. That's what they call a linear system. Everything's on the same line. Okay? So, well, I put my board away and started trying to write on the screen. Okay, so your x bar, that's what we're looking for, center of mass, is equal to your sum of the moments divided by the sum of the masses. Okay, now what are your moments? The first one, minus 50, right? 10 times minus 5. Notice they didn't give us units on any of this. You're just using them as if, and the units are just consistent. Our M2 is 0. Moment 2 is 0 because 15 times 0 is 0. M3 is a positive 20, and M4 is a positive 70. Okay? And all that's divided by your total mass, which is 10, 15 are 25, and 5 is 30, and 10 is 40. Okay? Whew. Goodness gracious. I really need, my eyes are dry. I think having the ceiling fan on, just drying out everything, my head, my throat, everything. All right, let's add these two together. 90 minus 5 minus 50 is 40, so that's be 40 over 40, which would be 1. So 1 unit to the right. Now I kind of wish, now I had drawn this, not that much, but let's go back and let you look at this figure here. If we moved the fulcrum, which right here is underneath the 15, can you see that? Move it to the right 1. Then this one over here would be 10 times 6, that would be a minus 60. The next one would be 15 times minus 1, that would be minus 15, that would be minus 75. Okay, I can't hold this any longer. Let's do the same thing here. This 5, so we had a minus 75 then, and if this 5 were 3 units away, that would be 15, and if 7 were 9 units away, whoa, that's not working out. No, I'm sorry, I said it backwards. The 10 was 6 units away, that would be 60, 15, and 60 is 75. 75 to the left, 75 to the right, that would have wound up being 0. So sure enough, if your X would have been the center of mass 1 space to the right of where it was, that would have given it to you. And sure enough, that's it. Now, let's go back to the book. Okay, back to current slide. Goodness, this thing's bouncing all over the place. Okay, so let's see how they did it. Okay, the moment about the origin being the center there, m1 times x1 plus m2 times x2 plus m3 times x3 plus m4 times x4. M1 was 10 times negative 5 would be a minus 50 plus 0, and this is the same thing we did, minus 50 plus 0 plus 20 plus 70, and that came out 40. Moment about the origin, the total was 40. Divide that by the mass, which was 10 plus 15 plus 5 plus 10, that also adds to 40, so your center of mass would be 40 divided by 40, which would be 1 length unit. Okay, see, being a physicist by nature and by training, I hate that they leave off the units, because the moment was a mass times the displacement, mass times displacement, mass times displacement, divide by the mass, you get a displacement. So that would be 1 displacement unit to the right. Okay. Note that the point masses would be at equilibrium when the fulcrum was located at x equal 1. We just did that. Now, rather than defining the moment of a mass, you could define the moment of a force. In this context, the center of mass is also called the center of gravity, which is a force type unit. So let's consider the system of point masses m1, m2, m3, all the way up to m sub n. that is located at x1, x2, x3 all the way up to x sub n. Then because the force, which is mass times acceleration of the system, the total force on the system would be capital F, total force is m1 times your acceleration. Now the whole system's moving, okay, moving together. So that would be m1 times a plus m2 times a plus m3 times a all the way up to mn times a, which if the total mass is m1 plus m2 plus m3 all the way up, then that would be m times a. Okay, basically Newton's third law. Now, okay, we got 10 minutes left. I think I can make it. Goodness, I'm dry. The torque, or the moment about the origin, is the force times its displacement from the origin. Not the mass times displacement, but the force times displacement, which is m1a times x1 plus m2a times x2 plus all the way up to mna times it, which is just your total mass of the whole system times the acceleration of the system. Then the center of gravity is total force, total torque, divided by the total force, which would be m0a, which is your center of gravity times your acceleration, divided by, excuse me, the total mass, total force, which is ma, little ma. So that's m, again, the moment, okay, and this now is your same moment we were talking about before, and that's your center of mass there again. So center of gravity, center of mass, same thing. Center of gravity, center of mass have the same location. So it doesn't matter which one you call. If your problem's set up with masses, not forces, it is technically a center of mass. If they're set up with forces, not masses, technically it's the center of gravity, but the calculation is the same. So let's move on to the center of mass of a two-dimensional system. Okay, this is on the top of page 497. Okay, you can extend the concept of the moment in two dimensions by considering a system of masses located in an xy plane at points x1, y1, x2, y2, x3, y, all the way up to x sub n, y sub n. Here is a two-dimensional drawing of such a setup. Rather than defining a single moment with respect to the origin, two moments are defined. One one with respect to the x-axis, one with respect to the y-axis. Okay? Now, each mass has a moment with respect to each axis. That's why there's two dotted lines. One's going horizontal and one's going vertical. Okay? Now, here is your two-dimensional system, the bottom line here. Let the point masses m1, m2, m3, m4, all the way up to m sub n be located at all these different points in the xy plane. The moment about the y-axis is the sum of all your moments, of all your masses, of the moments about the y-axis, which is all your masses times your x displacement, because x measures how far you are from the y-axis. If it's negative, you're over here. If it's positive, you're over here. So that's what your little x's stand for. Your m's are your masses, so just as before, but now that which we were calling the moment before, we're now calling the moment about the y-axis, because the y-axis is where 0 was on the one-dimensional scale. So then the moment about the x-axis would then be m sub x, which is your m1 times y1, how far it was above the x-axis, m2, y2. If that was below, that would then be a negative, whatever, all the way up to m sub n times y sub n. Now the center of mass, x bar, y bar, would then be, x bar would be the moment about the y-axis, which is 0 on the x scale. Okay, so it's m sub y over your total mass, and the y bar would be m sub x over your total mass. So the x bar would have moment with respect to y, y bar would be moment with respect to x, and where the total mass is the summation of all the masses. Okay. Goodness, I'm running out of juice fast here. The moment of a system of masses in a plane can be taken about any horizontal or vertical line. It doesn't have to be the x-axis or the y-axis. Any horizontal or vertical line. In general, the moment about a line is the sum of the product of the masses and the directed distances from the points to that line. So, let's have a horizontal line at y is equal to b. If the x-axis is down here, b is positive. If the x-axis is up here, b is negative. Okay, b is just some distance from the x-axis. So then the moment with respect to that line, that horizontal line y is equal to b, is m1 times y1 minus b plus m2 times y2 minus b plus m3 times y3 minus b, all the way up to m sub n times y sub n minus b. Okay, it's how far you are from that axis. The mass times how far you are from that horizontal line. Your m sub moment with respect to the vertical line, x equal a, you know, if this is the y-axis, you're over here, that's a positive a, over here it's a negative a. So moment with respect to something that's a units from the y-axis, m1 times x1 minus a plus m2 times x2 minus a plus m3 times x3 minus a plus all the way up to m sub n times x sub n minus a. Okay, now that's about the vertical axis, x equal a. Just trying to see why that line's shorter than the other one. I guess it's, I don't know, but it is, but it doesn't matter. All right, here's example 3. I think we have time for it. Find the center of mass of a system of point masses. M1 is 6, M2 is 3, M3 is 2, M4 is 9, located at 3, negative 2. And I think I will write these in just so you can get the idea. M1 is at this one, M2 is at this one, M3 is at this one, and M4 is at that one. Okay, there they are. Okay, now find the center of mass of the system, and they don't say with respect to any line, so we'll assume the axes. Okay, so M1 x1, that's from the y-axis here, so this is I better go, let's see, we're not going to finish. Okay, it's just going to take, it wouldn't take that long to write it, it's going to take that long. So let's pause here for a moment and let me get my pencil and mark that we're going to do example 3 next time. That's where we'll begin. Okay. Homework exercises here will be either 5 or 7. They're both at Calc Chat. 7's at Calc View. Number 9 is at Calc Chat. And if we had gotten that example done, you could have done more, but we'll stop right there and just stop either 5 or 7 and 9. Any questions on what we've done so far in 7.6? Hopefully it'll go a little faster next time. Fluid pressures and fluid forces, a very short section. So hopefully we'll finish 7.6 and 7.7 next time and get started in 8. And that's this week. The next week will be all chapter 8, okay? And wherever we stop, I'll give you your test for chapter 7, probably after class, sometime after class, probably Wednesday evening, because I've got another class right after this one. And then next week, whatever we get done in chapter 8, I'll give you that test. It'll be very short, very easy to do, and that will be the last test you have. And I can't remember when you have to have that in. I think it's Thursday of next week. Is that right? Does anyone check on that? I believe that's correct. And so I'll give you that on Wednesday, and you'll be able to finish it and get it to me hopefully by Thursday or over the weekend. I'll have to have your grades in, I think, on Monday of the following week. So last day we'll meet is Wednesday of next week, but get me the test then sometime after that. I'll get the test to you that Wednesday evening, hopefully. All right, any questions? We've used our time, maybe not wisely, but we used it up. So we'll stop the sharing. Any questions before I shut you down? All right, we'll see you then on Wednesday. Hello, welcome. Okay, let me get Roy here. And David here. Bottom part of the alphabet's doing quite well here. Top part has its, oh wait, here's some. Both of these. Nikaya. Yeah, I think it's Nikaya. And Valerie. All right, music even. All right, so we got 4 people here so far. While y'all are coming in, let me go down here and see. I only had less than 5 minutes between classes. Let me go down and get rid of some files here. This is one from the last class and the last class. Whoops. And this one. Okay. All right. Oh, here's some more coming in. Juan and Parisha. There's one. And there's Parisha. Okay. All right. Let me get back to trying to open up some more things for y'all. Okay, we're in chapter 23. Next to the last chapter we'll do. And it's going to get open in a minute. I'm trying to, yeah, we did get started last time in this chapter. It's taking its time opening. There we go. And this is where we left off. Cloud forming processes, that's where we were. So let's go from current slide. Okay. I don't think I need to do that quite yet. In just a minute. Okay, let me get back to Zoom. Okay, nobody knew. I was hoping someone would show up. So while we're waiting for them to show up, let's take our share screen to be here. All right. Now, can everybody, yuck, see my PowerPoint?
Yes, sir.
Good deal. Thank you. Okay. All right. Let me scoot this over so it'll be a little more out of the way. Roy's always in the way, you know. Okay. Now we'll go from current slide. Oh, wait. Nope. Wait. Sorry.